Welcome to the video for C5.2.1, where we're going to look at the introduction to rates of reactions. So for this start, I want to pause the video in a minute. We're going to do this reaction here. So we take magnesium and react it with acid, we get magnesium chloride and hydrogen. So if we do this, and if we assume that the magnesium is the limiting reactant, which is what we met in C5.1, and the HCl is in excess, then based on that, what would the effect of changing these conditions be? Now, you don't need to explain why. We'll get to that over the next series of lessons, but just from your gut instinct, what would you expect to happen? Okay, so pause the video and have a go at this, and then you can check your answers. Okay, so stirring the mixture, we would expect to make it faster. Cooling it down would make it slower. More concentrated would make it faster. Chopping it up would make it faster. Using bigger volume of acid, because the acid's in excess, that's going to be the same time, so it's not going to affect it. So there's some possible answers, but you don't need to worry about what the actual numbers. So learning objectives for today, we need to be able to explain what we mean by rate of reaction, suggest some practical methods for determining the rates, and interpret rate of reaction graphs. So we're going to use the word rate today in terms of chemistry context. But it's always useful to have a look at what it means in everyday language and see if we can relate this. So when we talk about crime rate, we're talking about the amount of crime that happens in a specific time. If we're talking about an hourly rate of pay, then that's how much money they get per hour. If you're asked to rate your ability at something, then that's just placing yourself on a scale, so that's not quite as useful for the chemistry. And increasing the temperature increases the rate of reaction. So this one here is not quite as useful. But in both of these, we're talking about how something changes over a period of time, and that's the same as the rate of reaction. Okay, so there's just a screen print of the dictionary definition of it. So we had a measure, quantity or frequency, typically one measured against another quantity or measure. So the crime rate, the hourly rate of pay, and that's most closely linked to the chemistry definition here. But we can also use it as a verb, so if you're assigning a standard or value according on a particular scale. So this one's not particularly useful, but this one's not dissimilar from our chemistry one. So our chemistry definition is that rate's a measure of the change in the amount of product formed over a given period of time. So you need to pause the video and copy that into your notes. Right, so how can we measure the rates of reaction? So if we have this reaction here, so we've got magnesium reacting with hydrochloric acid to give magnesium chloride and hydrogen. So always pause the video, look at the reactants and the products, and see if you can think of a way that we could measure the rate of reaction. Particularly think about what we did last lesson. Okay, so hopefully we've realized that one of our products here is a gas. In our last lesson, we looked at ways that we could measure the volume of gases, and we can use this to measure the rate of a reaction. So we can measure the volume of gas in three ways, just like we talked about last lesson. So we could use a mass balance, but this doesn't really work here because hydrogen's not very dense, so the mass change is going to be too small. We could use a gas syringe, or we could use upward delivery, which is okay for hydrogen because hydrogen doesn't dissolve in water, so we don't have the problem that we would if it was carbon dioxide. So we can use either of these two here. So it doesn't matter which method you get, what you'll end up with is a graph like this. So if you measure the volume of gas given off in a reaction, so if we measured the volume of hydrogen over a period of time, so this is just measuring it over 3 minutes, what you would see is that if you plot that on a graph, you get it gets very steep to start with, and then it levels off. So A is our fastest rate of reaction. Okay, so it's going to be quickest at the start, then it's going to slow down, and then at C, it's actually going to stop. So when the line becomes horizontal, that means the reaction stopped because we're not making any more hydrogen. The amount of hydrogen that's produced is not increasing, so the reaction has finished. All the reactants have been used up. And it's fastest here because the concentration of the reagents is highest at this point. Now, we haven't done the effect of this, but in the next lesson, we'll see that if you increase the concentration of the reagents or the reactants, that it increases the rate of reaction. So as the reaction progresses, some of those reactants get used up, and therefore the concentration is lower, and so the rate of reaction slows down. So you will always see this curve, which will then level off to a horizontal line. So if I want to work out the rate of reaction, it's going to be the gradient of the graph. So the units of the gradient, so remember gradient is the change in y over the change in x. So if we want to know the units, we just put the units of y, which is centimeters cubed, over the units of x, which is seconds. So that becomes centimeters cubed seconds to the -1. So if I want to calculate my mean rate, so I can do this in two ways. If I want to measure the rate over a period of time, so I'm measuring the time between 60 seconds and 90 seconds. So I'm measuring the rate over that time period. So if I do that, I can just draw a triangle between the 2 points, and it's the change in y over the change in x. And it's important to draw a big enough triangle here, because if we draw a small triangle, it's not going to be accurate. So if I do that, I get 12 divided by 30, which is 0.4. And what I'll find is if I do this at the start, so if I did the same thing here, I would get a bigger value. And if I did it here, I would get a smaller value because the rate decreases as the time goes on. So we've looked at why the reaction's fastest at the start, and that's because the concentration is highest at that point. So if I want to calculate the rate of reaction at a certain point, what I need to do is draw a tangent. Now, I can't very easily draw a straight line on here, but if I wanted to measure the rate, I would draw a tangent. Sorry, I can't do this on here. No, that's not a very good tangent. Let's draw it here. So if I was to draw a tangent there, so I can draw, in fact, this would work better if I've got a different colour pen, wouldn't it? Right, so if I wanted to measure so when I have the gradient of a curve, I draw a tangent at that point, and then I work out the gradient at that point. So I do dy divided by dx at that point. Okay, so I calculate the rate of reaction at a certain point. So I draw a tangent, and then I calculate the gradient at that point. And as we said on the previous slide, it's the units of y divided by the units of x. So it would be centimeters cubed over seconds to the over seconds, which would be centimeters cubed seconds to the -1. If we measured the mass of a product, then I'd have grams and then time. So it would be grams over seconds. So it would be grams per second. Right, so there's some exam questions on a PDF file. So if you work your way through those, try and answer them as best you can, and then the mark schemes at the end, so you can mark and correct your work.